Hello class, you're welcome to our physics class, and in physics we shall be looking at the topic electrical energy and power. Now this is a continuation of the topic current electricity. So what is the electrical energy and power about? Now a coulomb of a charge in a circuit is being carried from one point to another in a circuit by energy. So work is done to move a coulomb of charge from one point to the other. Now work is done and heat is produced when one coulomb of electricity or charge moves from one point to another with a potential difference across the point. So for instance, if you have a circuit such as this and you need to move a charge from one point to another, work is done to move the charge from this point to the other, and for work that is done there will be a potential difference across the points. So with all this, we have that the work that is done equal to potential difference multiplied by the charge itself. Now we know that Q equal to IT, so we can substitute this IT for Q in this equation, whereby we have V multiplied by IT. Hence, work is equal to IVT. So this is the formula which we shall be using. Now let us take note that this formula can vary depending on the parameters which we have. For instance, this W could also be equal to V squared over T R, or it could also be equal to I squared RT. And take note that you don't need to cram all these formulas. Reason being that, for instance, if you are not given I and you have VTR, what you can easily do is to note that I equal to what? V over R, according to the electricity formula. So if I equal to V over R, you replace this I with V over R, and when you replace this I, you would arrive at V squared T over R. Likewise, if you are not interested in V in the formula, we are aware that V equal to IR. So when you replace this V, you can put IR there. So you have I squared RT. So you have this. So there is no real need to cram. Next thing is electrical power. Electrical power produced is defined as the energy used per second. We mean that power equal to energy used, or which is work done over time. Now from here, we have that the work done is IVT. So if you have it as IVT over time, so time will cancel time, so you are left with power equal to IV. So this is another formula which we shall be using to solve questions under electrical energy and power. And take note that this is not the only formula. We could have it as P equal to V squared over R, or equal to I squared R, which does not need to be crammed as well. All you need to do is to remember this formula, and then you replace whatever needs to be replaced. Then it's worthy to note that commercially, electricity is measured in kilowatts, where power has the unit of watts. So electricity is measured in kilowatt hour, meaning that power over time, and 1 kilowatt hour is energy supplied by a rate of 1000 watts. 1000 watts per hour. Next, we move on to capacitors. What are capacitors? Capacitors are devices used mainly for storing charges. We could have two parallel plate conductors. So these are parallel plate conductors which are negatively and positively charged. So they carry charges, then they are linked by a battery. So we have this as a battery here. So we are saying that capacitors consist mainly of two plate conductors that are separated by a very small distance. So there's a small distance between these plates. The conductors carry equal and opposite charges by connecting them across the terminals of a battery, therefore having a potential difference of V across the plates. So we have a potential difference across these two plates. We have a potential difference, across them. And with this, we have that the charge is directly proportional to the potential difference. And so when we remove the proportionality sign, we'll have Q equals to CV, where Q represents the charge, this C represents capacitance, and this V represents potential difference. The unit of charge is coulomb. The unit of capacitance is microfarad. That is the SI unit. And we know that the unit of potential difference is the volts. So we said the unit of capacitance is farad, which we could have other variation of it, such as having microfarad, could have picofarad. 1 microfarad means 1 times 10 raised to the power minus 6 farad, and then 1 pico means 1 times 10 raised to the power minus 12 farad. Now another thing is this: if you have capacitors that are arranged in series, something like this, the total capacitance is gotten as 1 over C1 plus 1 over C2. That's the total capacitance. Whereas when they are arranged in parallel like this, the total capacitance is taken as C1 plus C2. So when they are arranged in parallel, so here we have series, and over here we have parallel. So we have C equal to C1 plus C2. This is the exact opposite of resistors. Now it's important to note that capacitors are used for storing charges. So electrical energy is stored in a charged capacitor, and the energy that is stored can be calculated by having W, which is the energy, equal to half CV squared, where C is the capacitance, V is the potential difference squared. Now this is not the only formula we can use here. We could also link it with half VQ, and it can also be linked to Q squared over 2C. So this is how we calculate the electrical energy stored in a charged capacitor. So in capacitors, these are the formulas that we shall be using. Next, we want to solve questions on electrical energy and power, and also capacitance. Question 1 says, how much heat is produced in 1 minute by an electric ion which draws 5.0 ampere when connected to a 100 volt supply? So we state our parameters. We are calculating the quantity of heat produced in 1 minute, and we have a current of 5 ampere and a voltage of 1000 volts. So we have that the heat produced, which is taken as W, work is done and then heat is produced, equal to IVT. The current in this question is 5, the voltage is 100, and the time is 1 minute. And let's take note that we'll convert this 1 minute into second because that's the SI unit. So 1 minute into second is 60. So when we multiply all this, we'll have it as 30,000 joules, which is the same thing as 30 kilojoules. It says a filament lamp is rated 240 volts, 60 watts. What does this mean? B. Calculate the current which is drawn from the lamp. And C. The resistance of the filaments. Alright, so we have a lamp, and in the lamp it's got some filaments which glows, and as it glows it produces heat. So the first thing we have to do is to find out what that statement means. Now, the statement means that a potential difference of 240 volts is applied across the filament of the lamp and it supplies energy at the rate of 60 watts. That is what the statements mean. The B says we should calculate the current. So let's state our parameters. We have that the power is 60 watts in the question, and we have a voltage of 240 volts. So we have that P equal to IV. P is 60, I is what we are looking for, multiplied by the voltage, that is 240. So I equal to 60 divided by 240. Alright, so we have 1 over 4, and that gives 0.25 ampere. So that is the answer for B. C says we should calculate the resistance of the filaments. What we need to do is, we have the power, and we said there are other varied formulas of power where we would replace this I with V over R. So we have this as V squared over R, right? So we have that if the power, so the power in the question is still 60 watts, and then we have a potential difference of 240 squared. Okay, then R. So R equal to 240 squared over 6, and that will result in 960 ohms as the resistance. Next question says an electric fan operates on a 240 volt potential difference. It is left for 100 hours on a current of 4 ampere. What is the total energy consumed by the fan in joules? How much does it cost to operate the fan if the electricity is sold at 5 kobo per unit, taking 1 unit to be equal to 3.6 times 10 raised per 6 joules? So in this question, let's state our parameters. We were given the potential difference of 240 volts, and we were given the time as 100 hours, taking a current of 4 ampere. Next is to calculate the total energy consumed by the fan in joules. So we are looking for the energy, which is W. First, let's convert this 100 hours into the SI units. 100 hours is 100 times 60 times 60. So we have 60 minutes and then 60 seconds. And this gives us 360,000 seconds. So here we have that the energy with which the work was carried out equal to IVT. Our current is 4, the voltage is 240, and the time is 360,000 seconds. And so this would give us 345 times 10 raised per 5, which we could approximate as 3.5 times 10 raised per 8 joules. Alright? Now in the question, so we've gotten the first part of the question, and that is the total energy consumed. Now the second part of the question says that we should find the cost to operate the fan. So if we sell at 5 kobo per unit. So worthy of note in this question is the fact that we're told 1 unit equals to 5 kobo. And this same 1 unit is equal to 3.6 times 10 raised per 6 joules. So in this question, we want to find the cost of 3.5 times 10 raised per 8 joules. So what we need to do is we take these two. Alright? We take these two. So we have 3.5 times 10 raised per 8 joules. What will be the price of that? So what we could do is to cross multiply, that is, this multiplies this and this multiplies this. So we have x multiplied by 3.6 times 10 raised per 6 equal to 5 times 3.5 times 10 raised per 8. Making x the subject of this equation, we have 5 multiplied by 3.5 times 10 raised per 8 over 3.6 times 10 raised per 6. When we solve 5 times 3.5 over 3.6, we will have 4.861. Then multiplied by this 10 raised per 8. When we bring this 6 up, it becomes minus 6. So here we have 10 raised power 2, right? So we have 4.861 times 10 raised power 2. We can approximate this 4.861 to 5 times 10 raised power 2. Hence, this is 500. So 500 kobo. 500 kobo is the same thing as 5 naira. When you change kobo to naira, you divide by 100. So that is the cost of the energy produced. Here, the next question says, a battery with EMF 24 volts and internal resistance 2 ohms is connected to an electric heater of resistance 4 ohms. Calculate A, the current in the circuit. B, the power input to the circuit. C, the power output of the heater. And D, the energy supplied by the heater in 1 minute. So let's state our parameters. We have an EMF of 24 volts. We have an internal resistance of 2 ohms connected to an heater, and the heater has a resistance of 4 ohms. So in this question, we have to calculate the current in the circuit. Alright, so we could have this as a sketch for the question. So we have this EMF here as 24 volts, and we have an internal resistance of 2 ohms. This is an electromotive force, but it is not the same voltage that we will have at the 2 points. But then with that, we can still calculate our current. So we have that current flowing in this circuit is V over R, which is equal to the EMF over R plus R. We will be making use of E and then R and R. So we have our E to be 24, and our R here is 4 plus 2. So we have 24 over 6. We have 4 ampere. So that is the current flowing in the circuit. B, we have to calculate the power input to the circuit. The power input to the circuit is the quantity of power being produced by this battery into this circuit is what we are interested in. So in that case, we have an EMF of 24 volts, and we have a current of 4 ampere. Hence, we could have it that our power equal to IV. So I is 4 multiplied by 24, and that gives us 96 watts. So this is the power input to the circuit. C says you calculate the power output of the heater. If you are to get the power output of the heater, we are going to make use of only the R, only the resistance of the resistor in this case, which is unlike B, because in B here we are using the capital R and the small r. Alright, so our R, that's the external resistance, is 4 ohms, and so we'll have it that the power output in this case equal to I squared R, because we are interested in the current as I, then R. We will not be using the voltage here. So we'll have it that our I is 4 squared, then R is 4 as well. So 4 squared is 16. 16 times 4 gives us 64 watts. So that is the power output. And from here we could quickly generate the power loss. The power loss will be 96 minus 64 watts, and that will be 32 watts as the power loss. Then this says we calculate the energy supplied by the heater in 1 minute. So D, to calculate the energy supplied by the heater in 1 minute, here we have the energy supplied by the heater equal to I squared RT. Now in this case, we are not using IVT, because when we look at the voltage, the IVT, the voltage we have here is this. That is the EMF. So we are using the R of the heater to calculate this. So our current is 4 squared, then the capacitance is 4, and we have a time of 1 minute, and 1 minute is same thing as 60 seconds. And so when we multiply all this, we will have 3,840 joules, which is the same thing as 3.84 kilojoules, which was gotten by dividing this 3,840 by 1,000. Here is the next question. It says that two capacitors of 1.0 microfarad and 2.0 microfarad contain charges 0.5 times 10 raised by minus 4 coulomb and 1.5 times 10 raised by minus 4 coulomb respectively. A. If these were connected in series, calculate the equivalent capacitance and the potential difference across the combination. B. If they were connected in parallel, calculate the equivalent capacitance and the potential difference across the combination. We have an idea of what the sketch will look like. So in A, if they are connected in series, what will be the resultant capacitance? Likewise, the resultant charge. So in the first case, the resultant capacitance. So if they are connected in series, so we have that 1 over the total capacitance equal to 1 over 1 plus 1 over 2. And when we add this, we will end up having 2 plus 1, that's 3 over 2. So the resultant capacitance here is 2 over 3 microfarad. To find the net charge is gotten by adding the two charges. The net charge, whether the setup is in series or parallel, is gotten the same way. So in both cases, we calculate the net charge by adding what we are given. Hence, the net charge equal to, we're given 0.5 times 10 to the power of minus 4 plus 1.5 times 10 to the power of minus 4. So we had this, since minus 4 is common there, since 10 to the minus 4 is common on the two sides, we can factorize it and bring it out and have 0.5 times 1.5. When we add this, we'll have 2 times 10 raised by minus 4. So this is the net charge. So we are told to calculate the potential difference across the combination. And here we have a formula that says that Q equals to CV. Now this is a formula that is related to the charge that is stored by a capacitor. So here our Q is the charge, which is 2.4 times 10 raised by minus 4. This is the same thing as 0.667 times 10 raised by minus 6 farad. That micro, this is it here. Alright, so we'll bring this in. I'll have 0.667 times 10 raised by minus 6 times V. So we have V will be 2.4 times 10 raised by minus 4 over 0.667 times 10 raised by minus 6. When we calculate this, we would end up having 300 volts. So this is the potential difference across the combination. B, we're told to calculate it when we have the capacitors in parallel. When they are in parallel, the total capacitance is the addition of the two capacitors, which is 1 plus 2, and that gives us 3 microfarad. Alright, and we said that the net charge remains the same, which is 2 times 10 raised by minus 4. So for us to calculate the potential difference across this combination, we have it that Q equal to CV. Our Q is the charge. So the charge is this, which is 2 times 10 raised by minus 4. And here is our C, which is 3 times 10 raised by minus 6. That is, the micro becomes minus 6 times the voltage, which is what we are looking for. So V equal to 2 times 10 raised by minus 4 divided by 3 times 10 raised power minus 6. And when we calculate this, we would have 66.7 volts as the potential difference. Alright, so this next question says, for the circuit shown, calculate A, the current through the ammeter, B, the potential difference across the 1 ohm resistor, C, the heat generated per second in the 1 ohm resistor, assuming the internal resistance of the cell is 0. Alright, so in the first instance, we have to calculate the current through the ammeter. First is to calculate the total resistance of these parallel resistors. So we have it as 1 over RT equal to 1 over 2 plus 1 over 2, and this will give us 1. So the RT here equal to 1. Then we have an external resistor here as 1. So the total will be 1 plus 1, and that is 2 ohms. We have an EMF of 4 volts, taking that the internal resistance is negligible, that is 0. So we have it that our current I equal to V over R, that is our voltage is 4 over 2, and so we are having 2 ampere as the current flowing through this circuit. The B part says we should calculate the potential difference across the 1 ohm resistor. Now across this 1 ohm resistor, if we have a potential difference across it, the potential difference across this will be to use the 1 ohm as the resistance and to have our current as 2 ampere. Hence, the potential difference is I times R, and that is 1 multiplied by 2, so that is 2 volts. That is the value of the potential difference across the 1 ohm resistor. Then the C part of the question says we should calculate the heat generated per second in the 1 ohm resistor. So we have it as W equal to IVT. I here is 2, and then our voltage is 2, and we have 1 as the time. So we have 4 joules per seconds. That is the heat generated per second. This question which says the net charge on a capacitor which is charged to a potential difference of 200 volts is 1.0 times 10 raised power minus 4 coulomb. What is the capacitance of the capacitor and the energy stored in the capacitor? So first, we state our parameters. We have a potential difference of 200 volts, and we have a charge of 1.0 times 10 raised power minus 4 coulomb. So we have to calculate the capacitance, and we have it that Q equals to CV. So the capacitance equal to Q over V. Our Q here is 1.0 times 10 raised power minus 4 over 200, which is the potential difference. When we multiply this through, we would have 5 times 10 raised power minus 7 farad, and we can change this into microfarad by saying 5 times 10 raised power minus 1 times 10 raised power minus 6 farad, and that is what? So 5 times 10 raised power minus 1, that's 0.5. Then 10 raised power minus 6 is microfarad. So that is the A part. The B part of the question says we should calculate the energy stored in the capacitor. The energy stored in the capacitor is taken as W equal to 1 over 2 CV squared. Here, 1 over 2, the capacitance in this question is 0.5 microfarad. So we have it as 0.5 times 10 raised power minus 6 multiplied by V. Our V here is 200, so we have it as 200 squared. So we have 1 over 2 is same as 0.5 times 0.5 times 10 raised power minus 6 times 200 squared. That is 40,000. Now when we multiply all this, we will end up having 1 times 10 to the power of minus 2 joules. So that is the energy stored in the capacitor. A 40 kilowatt electric cable is used to transmit electricity through a resistor of resistance 2 ohms at 800 voltage. The power loss as internal energy is what? So let's get this question straight. We have an electrical cable which is 40 kilowatts. That is power. Alright? It is used to transmit electricity through a resistor of resistance 2 ohms at a voltage of 800 volts. Now we should calculate the power loss as internal energy. We will consider this resistor as the reason for the power loss. So what we'll do is, using this R, which is the 2 ohms, we want to derive the current that is passing through the cable. So we have it that P equal to IV, and the power that is passing through the cable is 40,000 watts, and the current times the voltage, which is 800. So I equal to 40,000 over 800, and that gives 50 ampere. Now after that, we'll now have it that we bring in our formula for power, which is I squared R. That is, this R is the resistance of the resistor. So I here is 50 squared times R. The R here in this question is 2 ohms. So we have 2500 times 2. We have 5000 watts. So 5 kilowatts is the power that is lost due to the resistor. Hence, the real power that is used is 40 minus 5. That is 35 kilowatts is the effective power in this setup. Here's the next question, which says a working electric motor takes a current of 1.5 ampere when the potential difference across it is 250 volts. If the efficiency is 80%, the power output is what? Here we have an electric motor which takes in a current of 1.5 ampere and having a potential difference of 250 volts across it. Now we have a power output, and in this case the power output is mostly lesser than the power input, so meaning that more power is put in but we have a lesser output. So here, first thing is for us to calculate our power input. The power input into the machine is equal to IV. The current here is 1.5 and the voltage is 250 volts. And so when we multiply this, we will have 375 watts as the power input. Now, what is the output from this motor? Now, we know that by saying that efficiency percent equal to the power output over the power input. That is how we get, so that's what the efficiency percent is. So in this question, we're giving the efficiency as 80%, so that is 80 over 100. The power output is unknown, and the power input is 375 watts. And so when we cross multiply, x multiplies 100, then 80 multiplies 375. So we are left with x equal to 80 multiplied by 375 over 100. So we are left with an output of 300 watts. So here is the output of this motor. This question says the cost of running 5 60-watt lamps and 4 100-watt lamps for 20 hours if electrical energy costs 10 naira per kilowatt is dash. Here we have 60-watt lamp, which are 5 in number, and we have 100-watt lamp, which are 4 in number. Hence, how many watts will be used altogether by this lamp. We have 5 times 60, that is 300 watts, and by the 100 watts lamp it will use 400 watts. Now I want to calculate the costs for using these lamps for 20 hours. First, we'll get our total watts, which is 300 plus 400, and that gives us 700 watts. Now we want to calculate the kilowatt hour. So we have it that for 1 hour it will be 700 watts, but for 20 hours that will be 20 times 700, and that will give us 14,000 watts hour. And this can be converted into kilowatt hour by dividing by 1000. So we have 14 kilowatt hour. Now in the question we're told that 10 naira equal to 1 kilowatt hour. So what is going to be 14 kilowatt hour? What we'll do is x equal to 14 times 10, and that gives 140 naira. This next question says the diagram shows two capacitors P and Q of capacitances 2 microfarad and 4 microfarad respectively, connected to a DC source. The ratio of the energy stored in P to Q is dash. This is as simple as taking the ratio. So the ratio of the energy stored, the major values we are given is 2 microfarad and 4 microfarad. So the energy stored is the work done by P over the work done by Q. In this setup, the electrical energy stored in the capacitor is equal to 1 over 2 C V squared. Now in this particular formula, everything here is constant except the capacitance. So every other thing gets cancelled out, which is the voltage really, and then you are left with the capacitance for P and then the capacitance for Q. So capacitance for P is 2 and the capacitance for Q is 4. So we have 1 over 2. Hence, the ratio of energy stored in P to Q is 1:2. Now this next question, it says that in the diagram, if each of the resistors can dissipate a maximum of 18 watts without becoming excessively heated, what is the maximum power the circuit can dissipate? Now each of these resistors, each of them can dissipate 18 watts, right? That's the maximum they can dissipate. But we want to find out the maximum power that they can dissipate altogether, which is not done by adding the each of the watts together. It can't be done like that. So what we'll do is to find out the current that is flowing in this setup, and we'll use the parameters we're given, such as power, which is 18 watts in each of the 2 ohm resistor. So we have it that power equal to I squared R. Our power here is 18 and the current is I squared, then the R is 2. So we have 18 over 2 equal to I squared, that is 9 equal to I squared. So I equal to square root of 9, and that is 3. So we have 3 ampere of current flowing in this. Now what we'll do next is we want to find the power across the entire setup. We would calculate the total resistance, where for this parallel, that is 1 over RT equal to 1 over 2 plus 1 over 2, and that gives us 1. So the RT here is 1, and then the other resistor is also 2, so we have plus 2. So we have 3 ohms as total resistance. Now with that, we can now calculate the power, taking our current to be 3 ampere. So we'll use the formula that power equal to I squared RT, that's total R. So our I is 3 squared times our R, which is 3. So 3 squared is 9 times 3. So we have 27 watts as the maximum power that the circuit can dissipate. So here's the next question, which says the energy stored in a capacitor of capacitance 10 microfarad carrying a charge of 100 microcoulomb is dash. So we state our parameters that the capacitance equal to 10 microfarad and we have a charge of 100 microcoulomb. Now this is the same thing as 10 times 10 raised per minus 6 farad, and here is 100 times 10 raised per minus 6 coulomb. Now we have to calculate the energy stored using this information, and we'll look for a formula that will bring these two together, and that will be the energy stored equal to Q squared over 2C. Here our Q is 100 times 10 raised per minus 6 all squared over 2 times our C, which is 10 times 10 raised per minus 6. Now with this information, we have this squared, that will be then times 10 raised per minus 6 times 2, that's minus 12 over 2 times 10 times 10 raised per minus 6. This cancels this. Now this minus 6 come up here and it becomes 1000 times 10 raised per minus 12 minus minus 6, and we have 2 left down here. Now minus times minus gives us plus, so we have minus 12 plus 6. So we have 1000 times 10 raised per minus 12 plus 6, that is minus 6 over 2. So 2 here is 500. So we'll have 5 times 10 raised per 2 times 10 raised per minus 6. So our answer is 5 times 10 raised per minus 4. And the unit of the energy here is joules. So here is the answer to the question. This next question says, this diagram shows 3 capacitors, C1, C2, and C3 of capacitances 2 microfarad, 6 microfarad, and 3 microfarad respectively. The potential difference across each respectively are what? Alright, so what we'll do first is to have our total capacitance, and after we've gotten our total capacitance, we shall use that to calculate the potential difference across each of the capacitor. So the total capacitance, this is a series connection, and in this series we have it as 1 over C total, that's total capacitance, equal to 1 over 2 plus 1 over 6 plus 1 over 3. So here we have the LCM of 6. 2 into 6 is 3, 3 times 1 is 3, 6 into 6 is 1, 1 times 1 is 1, 3 into 6 is 2, 2 times 1 is 2. So we have 6 over 6. So we have 1. So the total capacitance here is 1 microfarad. Now with all this, alright, so after finding the total capacitance, next thing is for us to find the charge flowing through the circuit. And for us to find the charge flowing through the circuit, we have it that the charge equal to CV. The C is the total capacitance, which is 1, and our voltage is 12. So we have 12 microcoulomb. Let's not forget that our 1 here is micro. So microfarad, here we have microcoulomb here. So now we want to find the potential difference across C1. So the potential difference across C1 is Q over C. Our Q is 12 and our C is 2, and that gives us 6 volts. Potential difference across the second one, that's Q over C as well. Now the Q is 12 and the C is 6. So we have 2 volts. And then for the third capacitor, we have the potential across the third capacitor is Q over C, and the Q is 12 and our C is 3 microfarad. So we have 4 volts. So these are the potential difference across the 3 capacitors. This next question says a cell of internal resistance R is connected to an external resistor R. The condition for maximum power transfer is what? We have a cell of internal resistance R connected to an external resistance capital R. The condition for maximum power. Now the condition for maximum power is if the R here is equal to the R outside. So if the resistance in here and here are the same thing, then we'll have a maximum power.